This is the second day for section 3.5, and we're talking about finding derivatives of trig functions. From the activity the other day, you used your Math 8, your nderiv key on your calculator, to numerically determine what the derivative of the sine of x is. And after you plotted a bunch of points, I think somewhere in the neighborhood of maybe 24 points, you had enough data, you had enough numerical information to see that when you connected those dots with a smooth curve, that you ended up having a cosine curve. So the derivative of the sine is the cosine. And likewise, when you did the same thing with the cosine function and used your Math 8 key, and collected all that data, you could numerically see that pattern, once you drew that smooth curve, was negative sine x, right? It went down first instead of up. And that's because the cosine curve is sloping downward, and we're going to talk about that in a little bit. In addition, you made some mini anchor charts, and the mini anchor charts had you do the quotient rule to find the derivative of the tangent of x by rewriting the tangent as sine over cosine, and you came up with secant squared. And likewise, using the quotient rule on the mini anchor charts, you found the cosecant is minus cosecant cotangent, and the secant is secant tangent, and the cotangent is minus cosecant squared x. So these are the derivatives for the 6 trig functions. The first 3 here, sine, cosine, tangent, are really common. We use those all the time, as well as the derivative of the secant. So those are definitely the most prevalent ones used. Cosecant and cotangent are used occasionally. So these are the 6 derivatives. These 3 I recommend just memorizing. Actually, these 4 maybe, but you can see some similarities. For instance, if we look at tangent and cotangent, they both have their derivatives are squared. If you notice, everything that begins with a C, cosine, cosecant, cotangent, all of those derivatives are negative. Secant and cosecant have the same pattern of having a derivative that's 2 trig functions. So there's ways we can kind of memorize all 6. So looking at our exploration results here. So this is again from that numerical exploration we did with Math 8 on our calculator. So there's our results, and we're going to look at these just a little bit differently. I didn't have to have you graph all those points, but getting numeric answers is easy to do with a graphing calculator. But we're going to look at the derivatives of trigonomic functions, our essential question here. What are they? And we're going to look at this through the use of just the slope of the curve. So for instance, here is sine of x. And so if we look at the slope of this curve, we can see that it starts sloping upward. In other words, it has a positive slope, so it has a positive derivative. We know that the derivatives are 0 at hills and valleys. So we're going to set up just a few derivative values. For instance, right here at this location, we have this derivative here. It's sloping positive. And if we zoom in, and this is kind of one of your web-assigned questions, one of your homework questions, if we zoom in on this area, it actually looks pretty linear, and it looks like it has a slope of 1, and it actually does. And so what I'm going to do, if you notice, there's a dot that popped up right here. I'm going to use this y-axis to graph the derivative on as well as the function. So I graphed a value at 0, 1 right there. So that's the first derivative, the value of the derivative at this location, slope of 1. So now I'm going to look at this location here, pi over 2. We know that the curve flattens out here, so we know we have a derivative of 0. So I'm going to graph a value of 0 right there. And then if this is 1, then you might be able to guess what the derivative or the slope of the curve is right here. At pi, it's sloping downward, so it's got a negative slope. And its value is also 1. So this value of this derivative is -1. So I'm going to graph a derivative value of -1 on my y-axis. And then this next location, we know that we have a flattening out of the curve, and we have a valley. So we know that derivative is 0. So I'm going to graph a value of 0 there. And then coming back to 2 pi, which is where the pattern, the sine curve starts over again, starts to repeat itself. Again, this is a slope of 1. So I'm going to graph a derivative value of 1 here. And so if I connect these with a smooth curve, that smooth curve looks like that. And that is, if it starts a value of 1 and goes to 0 and -1, that is the cosine curve. So we can look at this just by looking at the slope of the function itself instead of graphing all of those points. It was just easier to graph those points close together to actually see the shape of the curve. And so we're going to just run through this now real quickly for the cosine function. So again, this is a hill. It's just, you're only seeing half of it because I didn't extend the graph into the fourth quadrant. Also top of a hill here, because we know that the cosine is going to start repeating itself at that point. And this is a valley. So we're going to graph some values of the cosine, the derivative of the cosine here. So at this location, the derivative value is 0. So we're going to graph a 0 value. At this location, we're sloping downward. Notice the cosine function starts out sloping in a negative direction, right? It's sloping down. So we're going to start out with a negative derivative. So this is a derivative of -1. So we're going to graph a value of -1. Here, again, we have a flattening out of the curve, so we know that that's a slope or a derivative of 0. We're going to graph that value. At this location, we're sloping upward, so we have a derivative value here of 1 because the slope of that is 1. So we're going to graph a value of 1, and then up here again we have flattening out, so we have a derivative or a slope value of 0. So there's that value. So when I graph this and draw a smooth curve, connecting those dots, we see that it looks like sine, but sine would start going up and then coming down, and this starts in the opposite direction. So we have a negative sine function here. So we know the derivative of cosine is negative sine. So we can also kind of get the basic shape of that derivative just by looking at the values of the steepness or the slope of the original function. So this is a common application here, and that is since trig functions their pattern tends to repeat itself. That means it's well suited to model things like oscillation, or we might call this, if we were in physics, we might call it simple harmonic motion. And so a couple of things we just need to familiarize ourselves with, and I'm just going to use the sine function as the function here. I could have done a cosine, like this is a cosine. This is a negative cosine, but they're just offset by pi over 2. But we have to remember what the coefficient a stands for. Like if this were a 4 or a 5 or a 2, and that stands for the amplitude. So if you look at these drawings here, this trig function, its center is along 6, and then the hills are up at 8, and the valleys are down at 4. So this blue function here, with the block moving horizontally, this represents the position of that block, and its amplitude is up 2 and down 2. So that would be like 2 sine t. And then this is also showing, you can do this vertically too, where you have a spring and a mass hanging on it, and when it's not in motion, it just kind of extends the spring a little bit. But if you pull it down and then release it, then it starts to oscillate up and down. So again, that displacement from that, we call this the equilibrium point if we were in physics, but that displacement from the center line is that amplitude. So we pulled it down a distance a, and so it swings up and down a distance a from that starting point or that equilibrium point. So we're going to use this as a position function. and then we're going to use our higher order derivatives to find velocity and acceleration. And so likewise, here's another example of harmonic motion or oscillation, like, it's kind of like somebody swinging on a swing. So this pendulum motion also is something where you can model it with a trig function. So let's say that the position of this, let's say this swings back and forth by 5 centimeters to the left and 5 centimeters to the right. So we can model that then with 5 sine t. And so its amplitude would be 5. So if this is the position function, and remember position is s of t. I know s is a little confusing, a confusing variable to use, but s stands for position. So if I want to find the velocity, then I'm going to take the first derivative. And so the first derivative of 5 sine t is 5 cosine t. And then if I want to find the acceleration, I'm going to take the derivative of this. That's our higher order derivatives. So the 5 is just a coefficient, so we're going to bring the 5 down, and we're going to take the derivative of cosine, which is negative sine. And then we're going to do a little rearranging. We're going to call that minus 5 sine t. And then we're going to take the derivative one more time. And this is a new one. This would be the third time we've taken the derivative. And we call this jerk. And so if we take a derivative of this, the minus 5 is a coefficient. We're just going to bring that down. Derivative of sine is cosine. So we get minus 5 cosine t. And the jerk is, if you can kind of think about driving in a car, and let's say you're on an on-ramp to a highway. And so you get on the on-ramp and you really punch the accelerator to the floor, and you feel yourself, whether you're driving or in the passenger seat, you kind of feel yourself getting pushed into the seat. That sensation of being pushed into the seat is acceleration. That's literally the car propelling you or the car pushing you forward. That's acceleration. So let's say then you get to the end of that on-ramp, and so you're really accelerating because you got your accelerator pushed down to the floor. But let's say you get to the end of the on-ramp and you got to slam on your brakes because you are getting on the highway and it's rush hour and everybody's at a standstill. So the slamming on of your brakes is the jerk. So the idea is you slam on the brakes and you no longer feel yourself being pushed into the car anymore. You get jerked out of your seat, which is why they call the derivative of acceleration jerk. And it's that quick change in acceleration. The quick change in acceleration is transitioning from pressing down on the gas to pressing down on the brake. And that change in acceleration is called jerk, and it literally does jerk you out of your seat, especially if you hit the brakes really hard. So this is the jerk. It's how your acceleration is changing. And so if we count this, we started out with this function. This velocity is the first derivative. The acceleration was the second derivative of position. So jerk is the third derivative of position. So the definition of jerk then is a sudden change in acceleration. Anytime you see the word change, the instantaneous change is the derivative. So it's a derivative of acceleration with respect to time, which is the third derivative of position with respect to time. So that's kind of the meat and potatoes of day 2 is working with those higher order derivatives and talking about jerk. So just kind of a quick summary here. What are our derivatives of trigonometric functions? You want to memorize sine, cosine, and tangent. And you want to use, you can use the quotient rule for tangent and the other 3. And there's some patterns to memorizing these as well that we discussed a little earlier in the video. So at this point, you should be able to work on, there are 6 practice problems in your notes. And I'm going to go through the practice problems just step by step. I'm not going to, but what I would suggest is that you turn the video off right now and try them, and then use this video for checking your work. So the first example is practicing how to take the derivative when you have a polynomial times a trig function. So this is a product rule. So we've got a product of a polynomial and a trig function. So I put the product rule over here for you to remember. So it's a derivative of the first function times the second plus the first function times the derivative of the second. So we'll take these one at a time. The derivative of this, x cubed, is 3x squared. And then we're going to multiply that times secant, plus. Now we're going to take x cubed and multiply it times the derivative of secant, which is secant tangent. And so this is the derivative, and we don't have to simplify it. I mean, you could, but you don't have to. Let's look at the next one, also a product rule. We've got two terms. We've got 6x squared plus x cotangent x. So for this second term, we have to use the product rule. So we're going to just take the derivative term by term. The derivative of 6x squared is 12x plus, now get ready for the product rule here. The derivative of x is 1 times cotangent x, that's the derivative of the first times the second, plus first times derivative of the second is going to be x times negative cosecant squared. That's the derivative of cotangent. So here's your derivative. Again, not much to it after that. You can simplify a little bit. I would recommend maybe dealing with this product right here and getting the minus sign out front. Maybe simplifying this. 1 times cotangent is cotangent. There's the minus sign, x cosecant squared x, but totally up to you if you want to simplify that or not. The next one, also a product rule. Cosine x times sine x. And so again, we're going to use the product rule here. So the derivative of cosine is minus sine, and then times sine x, plus, we're going to bring the cosine down there, times the derivative of the sine, which is cosine x. This you might want to simplify. These are common multiple choice questions. So you won't see the answer in this form. What you'll see is that they combined the sine x times sine x to sine squared x. So this is minus sine squared x, and they did the same thing with the cosines, plus cosine squared x. So this is how you're going to see the answer form in a multiple choice type of question. Just a quick note, this is not equal to 1, right? This would have to be positive in order for this to be some sort of identity. So that's definitely not equal to 1. Another product rule. And this is a little tricky, but differentiating tan squared x. So what I'm going to do is we have a derivative for tan x, but we don't have a derivative for when we square tangent. So I'm going to rewrite this as tan x times tan x. So, and I probably should have put that in the video here. So we're going to think of this as tan x times tan x. So if this is tan x times tan x, then the derivative of the first is secant squared times tan x plus the first tan times the derivative of the second one, which is secant squared. So we're going to use a product rule, and that makes finding the derivative a little easier. If you notice, we have the same term listed twice, so I'm going to simplify that. Oh, there it is. There's the rewriting. It was just out of sequence. So derivative of the first times the second plus the first times derivative of the second. So now I can combine these because these are like terms. So I have 2 tan secant squared x, or 2 secant squared tan x, is however you want to write that. And again, the simplifying here is because if it's a multiple choice question, this would be the answer form that you would see. So this example is using the quotient rule now. Sine of x divided by 1 plus tan x. And these we do the quotient rule and we don't really simplify too much. So remember, our quotient rule is low d high minus high d low. Wow, that's a bad typo. That should be minus. So low d high minus high d low. So low is this, 1 plus tan x. D high, so the derivative of this is cosine, minus high, so we got sine x here, d low, derivative of 1 plus tan x. Okay, if we take the derivative term by term, the derivative of 1 is 0. The derivative of tan x is secant squared. So the derivative of 1 plus tan is just secant squared. It's 0 plus secant squared, but we don't have to write the 0. So that's the top. The bottom is low squared. And we just leave it like this. We don't expand the bottom. The only time we simplify and work with the bottom is when it's one term. And this is the derivative. We just leave it like this. We don't have to worry about simplifying it at all. And then the last one, again, bad typo, there should be a minus sign here. So let's find the derivative of tan divided by sine plus cosine. So it's going to be low, so sine plus cosine, times d high, which is secant squared, minus high, which is tan, times the derivative of the low, and we have to take the derivative term by term. So it's going to be the derivative of sine, which is cosine, plus the derivative of this, which is negative sine. So it's going to look like that, cosine minus sine x, and then all over low squared. So sine x plus cosine x quantity squared. And again, no need to simplify this. So at this point, after you've gotten done practicing those 6 practice problems, you can start finishing up the homework for 3-5. Remember, there's 2 days, day 1 and day 2. Or you can take the proficiency quiz in Blackboard if you'd like.